Let us discuss our findings, which went pretty well. It's hard to it's hard to apply this because you've got to keep the direction of current in mind, and then you've got to take into account what direction that will be flowing through the coils. But that said, this went pretty well. So the big things I wanted you to note are the comparison of what happens with a north and a south pole under similar motion. So let's recap that. Let's take, was it number 1 and 3, I think? Yeah. So the north pole entering the coil versus the south pole entering the coil. What differences did you notice in that?
In the south pole, when in it was negative.
Okay, and the north pole?
Positive.
It was positive. So the sign of the current changed, which meant the current was going in opposite directions in this coil. And what about when the north pole went in versus when the north pole came out?
When it went in, it was positive. When it went out, it was negative.
Okay, also opposite results or opposite directions. So this is hard for us to measure, but once we get these concepts in, it'll actually be fairly easy for you to figure out what's going on. So I saw several people with the correct drawing. So I want to draw up what's happening within the coil, and then we'll discuss at least a good way to predict that. Not necessarily the why to a really high extent, but sort of a why of how to think of it. So here is our coil. And let's picture that we have a north pole coming in, like so. What you observed is that this coil would react. And as long as this, oh, by the way, what happens if I just put anyone observe this? What happens if I just set the magnet inside? It's zero. So this only works when the magnetic field is changing, when the magnet is moving. So when this is moving towards it, what we observed is that the coil will actually react and make its own magnetic field this way. Now, right-hand rule, I know that this means that the current in my drawing would be going down, because that's going to make a magnetic field inside the coil that fights it. Furthermore, if I do the same thing, but now move a south pole towards it, I get the exact opposite reaction. I get a south pole facing this, so the magnetic field is actually reversed, and the current is reversed. Same thing happens if I have a south pole receding or a north pole on the bottom receding. Make sense? Kind of, you can see what's going on. Every time I do something, this coil fights me. This is what being a teacher is like. Something to laugh. Whatever is changing about your coil, so whatever is changing outside your coil doesn't want. And it will set up, that induces a current in the coil that will counteract it. We'll see, I'll probably set them up maybe at the beginning of class next week. But this is how a generator works. Because consider you have something mechanical that will continue to move this magnet in and out. Well, you'd be setting up current in here that would keep going back and forth.
Here are the following sports announcements for the day. The softball games against Cass and Manorville have been rescheduled for Monday, April 27th. The baseball C game against Cannon Falls has been postponed. The baseball 7th and 8th grade games against Byron have been rescheduled for May 7th. Softball varsity and JV will practice at 4:30 in the middle school gym. Boys JV and varsity golfers, please see Coach Bester after school. Varsity baseball practice will be in the middle school gym at 3:15, and JV baseball practice will be in the middle school gym at 4. There is no 9th grade baseball practice today. Thank you.
So the key for this is what we call Lenz's law after its discoverer, that a changing magnetic field will induce, which means create or force, a current in a loop of wire, or in a solenoid, what we saw, in a direction so that that loop's current will produce a magnetic field that fights it. Oh, that's hard to write. In a loop of wire, in a direction that creates its own magnetic field. To fight the change. This means that if there is not a magnet inside the coil doesn't want a magnet inside it. And if there is a magnet inside the coil, it doesn't want that magnet removed. If you are mechanically strong enough to do it anyway, you're going to make a current in here that's, if you're going back and forth, the current will be going one way, then the other, one way, then the other. That is called alternating current. And essentially, this is how 90+% of our electricity is formed. The only real case that doesn't produce electricity in alternating form is photovoltaic solar panels, so the black solar panels that you see sometimes. Those are direct current. Every other way, windmills, turbines, no matter how they're fueled, are spinning a magnet inside a coil.
What about blue solar panels?
The blue ones? I'd have to see them to be sure, but I bet. Oh, well, they're dark blue, black. They're nearly black. They're silicon. They're silicon.
How does the water thing